So actually, the large H, right? So we are making some hypothesis, making some assumption. Large H means one type of assumptions. Say the hypothesis or the prediction, the relation between data and output is linear, right? So linear is a large H, is like a large assumption. And what is a small h? Small h is a type of large h, right? It's a type of a linear function. So if we make large h linear relation, then small h can be just one type of linear function. Remember in the last lecture, so it's like when we are trying to find the relation between x and y, and we say, okay, y equals ax plus b. You say when we say something like this, we are making a large H hypothesis. So that means like we are assuming y and x is linear, right? It's linear to each other. And a small h is just a specific case in the large H. For example, small h can be y equals 2x plus 1, right? And so this can be called small h1. So it's just one hypothesis, right? And another hypothesis under the large assumption, right? So under this assumption, we can have multiple hypothesis function. So another hypothesis function is y equals to maybe 3x minus 2, right? So these are all kinds of linear function, right? But the large H is that we assume the relation between y and x is linear. And remember loss function, right? So whenever we determine that we want to use this small h, right? It can be h1, h2, or h3, whatever, right? So you use h1, and then based on x1, y1, right? So you apply h1 on x1, right? And you compare to y1, and you get a loss, right? And then you compare and you use h1 on x2 and compare to y2, and you also get a loss, right? And you use h1 on x3 and you compare to y3, you still get a loss, right? So you get a loss for h1, right? So this is a specific like a hypothesis functions. And of course, using hypothesis function h2, we can still get we can still like do the same thing, right? Apply h on x and then compare it to y. So h is our hypothesis function. It is what we use to predict, right? So we use h to predict y, and we apply h2 on x1, x2, x3, and compare it with y1, y2, and y3, right? And if they disagree, then our loss increased by one. And if they agree, then we get a loss of zero, right? So we can calculate the total loss. So in this case, you get a loss for H2. So we found the pattern, right? So whenever we make an HI, right? So HI belongs belongs to large H, right? Large H is what we call the hypothesis class, right? This is i.e. we can make an assumption that the relation is linear or quadratic or whatever, right? So this is the basic, the general hypothesis. And HI, small hi here, is a specific hypothesis. It's a specific function that we already determine the coefficient here, right? So for large h, we don't determine the coefficient. We just say it should look like this, but the coefficient is yet to be determined. But for small h, you are giving a specific coefficient, and you can use small h to calculate. For large h, you can't even calculate the loss, right? Because you don't know what coefficient a is, what coefficient b is. But for all the small h, you can calculate the coefficient. So then we say for each, right? For each hi, we have a loss hi, right? So for each hi, we can compute the loss as long as the hi is set, right? As long as you give me hi, we can calculate the loss by doing this, right? And then we get the loss for h1, get the loss for h2, get the loss for h3. Then we just select a specific a specific hi that minimize the loss, right? For example, h1 has a loss, h2 has a loss, and h3 has a loss. If the loss for h3 is the smallest one, then of course we will choose h3. So say h3 attains the smallest possible loss among all HI in H class. Then what do we claim? We claim H3 is the best, right? The best. So if H3 attains the smallest possible loss among all HI in H class, we claim H3 is the best prediction function, right? Or hypothesis function. Yeah, hypothesis function under the assumption class H, right? Maybe H is linear. So if you assume the relation is linear, then we have a bunch of linear function, right? And of course, one of them must be the best. And if it's H3, we say H3 is the best, right? It's the best function under the assumption that x and y is linear. And of course, it is not the best if we don't make any assumption, right? So that is no free lunch theorem. So no free lunch. So what is no free lunch theorem? Let us review again, right? No free lunch tells us if you want to find an optimal HI, right? If you want to find a specific HI that minimizes the loss, right? Which minimizes the loss, you must assume a an H, right? An H class. So you must assume an H class. So what is an H? So that H means like the specific like a pattern, right? A pattern or relation between X and Y, right? So you can say, oh, I don't assume any relation between X and Y. They can be either linear or quadratic or like a exponential or logarithm or whatever, or like a sin Y equals sin X, Y equals cosine X. So I don't make any assumption. Then you can't find this optimal H. Why? Because you have like an infinite number of HI and you just can't search, right? But if you say, oh, so we make an assumption it is linear, then you can write a small, so all the small h takes this format, right? So even though we still have infinite number of small h taking this format, but as long as this format is set, we have some mathematical tools to find, right? Have some mathematical tools to find what is optimal for coefficient A and what is optimal for coefficient B. How do we determine if it is optimal? So we just want to set a value for A and a value for B to minimize the loss, right? To minimize the loss. So to minimize the loss, we can of course take derivatives, right? So we can take derivative with respect to A and take derivatives with respect to B, and we will find the value of A and the value of B that minimize the loss. It's just that simple, right? Yeah. Okay, so this is a big idea, and this is a fundamental idea of no free lunch theorem, and what is like a what is a hypothesis, right? What is a small h and what is a large h, right? What is a hypothesis class and what is a hypothesis function, right? Hypothesis class says something about the whole relation. It's linear, it's quadratic, and hypothesis function says something about like what linear function it is, right? Is it 2x plus 1, 2x plus 3, 2x plus 5, 3x minus 2? You need to give a specific hypothesis function, right? So this is small h, and we have a lot of small h, right? And among those small h, one of them is the best. So we say that is the best small h with respect to this large h, right? With respect to the function the assumption we made. Okay, so that's my explanation for this first part, and maybe Chloe, can you read this part? Yeah.
This second step is the actual learning process and often, but not as always, involves the optimization problem. Essentially, we try to find a function h within the hypothesis class that makes the fewest mistakes within our training data. If there is not a single function, we typically try to choose the simplest by some notion of simplicity, but we will cover this in more detail in a later class.
Okay, cool. It actually supplements a very important point, which is the simplest, but and the simplicity. So This is what we will later encounter is something called regularization. But for now, let's just ignore this stuff. So it seems I already explained on the second stuff, right? So essentially, we're trying to find an edge with a hypothesis within the large H, right? Large H is a hypothesis class that makes the fewest mistakes. So what does it mean by making the fewest mistake? Chloe, can you explain this? Like in plain word or in your understanding. So what does it mean for to choose an age that makes the fewest mistake?
Like high accuracy.
Yeah, high accuracy. And if we explain in terms of the loss function, it makes what it makes a small loss, right? Because whenever we make a mistake, our loss increase. Remember that, right? So we make a prediction on x1, right, using h1 and compare it to y1. If h1 x1 does not equal to y1, then what? Then we make a mistake and our loss increase by one, right? So by making fewest mistake, we are also referring to, or it is equivalent to making a small loss, right? Making a as small loss as possible, right? So few mistakes means small loss, right? So we already so in last lecture we already see a definition of loss looking like this, and we'll review it again in this lecture. So now you should have a very concrete idea of what is a small h, right? Small h is just a one hypothesis function. It's a very specific one. So for small h, it has to be specific enough so that you can calculate it, right? So that you can apply it on an h. You can apply it on a data point x and get the actual value, right? So apply h on x1 and get a value and compare that value with y1. Y1 is the answer, right? So if you compare it with the y1, the answer, you find they agree, they are consistent, then you did not make a mistake and you did not increase the loss. But if you make a mistake, you will increase the loss. And the loss can be calculated in multiple ways. In the last lecture, we introduce the zero one loss, which we will review again in this lecture. And into this lecture, we'll spend quite a lot of time on another loss, which is more difficult to calculate it, but it enjoys better mathematical properties because it is continuous and so it can make derivatives. So function like this, of course, function like this is not differentiable. I don't know how many of you know the words differentiable. So, Mark, can you explain? Do you know the word differentiable and why is this loss function not differentiable?
I mean, like, I know how to differentiate stuff, but I don't really understand what it means.
Okay, yeah, let me draw. So, I mean, like when you do the calculus, you will see something like a function, right? A function like this is x and this is y. And our loss function is similar to this, right? So if loss function looking like this, right? So when more data points is added, the loss function increase, right? So if it looks something like this, then of course it can be differentiated, right? So you see it's continuous, it's smooth, right? But in 0, 1 example, you see it is something like this. So of course in calculus, you know that a function like this, right? Function like this is not even continuous. So of course it's not differentiable, right? In order to find the derivatives for a function to be differentiable, it has to be continuous first, right? So, but even if it is continuous, it may still not be differentiable because you can still have something function like this, right? So at this point, the function is not differentiable. You cannot find derivatives, right? Yeah. And if you don't understand this, it's fine. I'm just saying that so for those who understand the derivatives, I'm just saying that the loss function looking like this is jumping between 0 and 1, right? So like if you change h, some 0 just jumps to 1. It's not continuous change, so it's not differentiable, right? Differentiable is using derivatives to find the continuous change, right? To find the speed of change, right? To find the speed of change. But if your change is not even continuous, It's not smooth. Your change is not smooth. You cannot find the speed of change. Yeah, it's jumping. Yeah. So that's why we sometimes prefer a loss function like this, because a loss function like this, you see this is a quadratic function. So quadratic functions, when you plot it, it looks something like this, right? It's very smooth. You see it's smooth change, and you can find derivatives everywhere. Yeah. But let's still go back to the go back to the to here. Yeah. So okay. So now we have a more concrete understanding of what's a hypothesis function. What is a hypothesis class, right? This is the large assumption we made. And how to use small h to find the loss function. This is very important, right? We have practiced it in the last lecture, right? Remember that in this example, right, we give a concrete example for what h is, right? So h, right, this is one example of small h. And in this small h, we use h to make predictions, right? Make predictions, and we compare the prediction our prediction with the actual label, right? With the actual label, so like the 101 is the actual label. Yeah. So we compare our prediction with the actual label, and we say, oh, we get it all correct, then the loss is zero, right? So we also need to see how to find the loss. Okay. So cool. This is very important stuff, so I review it again and again. But let's continue to this. Okay, so this is quite long. Maybe Phoebe, can you help read this paragraph? Yeah.
There are typically two steps involved in learning a hypothesis. How can we find the best function? For this, we need some way to evaluate what it means for one function to be better than another. This is where the loss functions act a risk function comes in. A loss function is evaluated by hypothesis H on our training data and tells us how bad it is. The higher the loss, the worse it is. A loss of 0 means it makes perfect predictions. It is common practice to normalize the loss by the total number of training samples, and so that the output can be interpreted as the average loss per sample, and it's independent of n.
Yeah, very good. So let me explain this symbol, right? So for this symbol, it can be read as belongs to. So it means small h belongs to large H, right? H belongs to capital H. So why we say belong to? Because large H is a broad class, right? It means linear. And small h is just one type of linear function. It's a specific type of linear function, right? Linear means ax plus b, and a specific one can be 2x plus 1. So we say small h belongs to capitalized H. Yeah. And also, what does it mean by normalize? So normalize just means divide by n. Remember that in our example here, so we have already encountered it. So if we predict all three stuff wrong, right? So then loss is 1 plus 1 plus 1, right? So each time we make a mistake, we plus the loss function by 1. But since in our example, there are three samples, right? The sample size is 3. So we have 3 samples. Well, actually, it's not 3 sample. We have 1 sample, but the sample contains 3 data points, right? We have 1 sample which contains 3 data points. Yeah, so the sample size, yeah, the sample size is 3. So by normalize, we need to divide by 3. If the sample size is 5, then you need to divide by 5. If the sample size, which means n, right? If the sample size, you have x1, x2, x3, dot, 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 xn, right? So if you have n points, you need to divide by n so that you can get the average loss, right? Because, so what will happen if we do not divide by n? This is something to think about, right? So maybe Hector, can you give a like guess or thought on that? So what happens if we do not divide the loss by n?
I don't know, like we can't know how much like percentage we get correct or get wrong with.
Yeah, that's a valid point. So we can put it this way. So if you do not normalize, you do not divide by n, what happens if the n increase? And of course, you will make more mistakes, right? So if your sample have only 3 points, 3 data points, you can make at most 3 errors, right? So your loss can be at most 3. But if your samples, your training, right, your training samples have 100 data points, you can easily make 10 mistakes or 20 mistakes, right? I mean, making 20 mistakes out of 100 points is actually quite good, right? You are only making 20% of mistakes, and you are getting 80% of data right. But if you don't normalize it, you get a loss of 20. And in the case when you only have like 3 data points and you are making 3 mistakes, you get a 0 score, right? So you predict everything wrong, but your loss is only 3. This is unfair, right? So and actually, so it's like we are predicting with 80% accuracy, and you are predicting with 0% accuracy, and you only get a loss of 3. We get a loss of 20 only because we have more data. This is unfair, right? So we should divide the total sample size. Does everyone get this? Yeah. So this is the point. And also, what makes it even more unfair? So in machine learning, we know that the more data you train, the better result you should get, right? So YGPT is so good, so good at like making like a inference, making a like a conversation with you, because GPT is trained with tons of millions. It's like tons of data. It's like a billion, not even billions, like billions of billions, like trillion, right? Trillions of data, thousands of trillions of data. Yeah. So the sample size is huge. It's tremendous. But if we don't normalize it, if you train with a tremendous data set, you get a really huge loss, right? And we should not be penalized when we have a tremendous data set or training set or sample size, right? Actually, we should be rewarded, right? Because the more data we train, it's just like GPT. The more data we train, our model will get better results, right? So the more data we train is a good thing, right? Like if we train with tons of data, it's a good thing. So that should be reflected on our loss function, right? So that's why we normalize it by divide n. So if we train by 10,000 data, then we divide it by 10,000. It's a good thing. So if we only make one mistake, the loss is only 1/10,000, right? It's not like you are only training with 10 data and you make one mistake, then your loss is a 1/10, right? It's much larger than 1/10,000. Why? Because 10 data is not good as 10,000 data, right? So if you say you are a consumer, you are a customer, and you are you are like you are making purchasing decision between two machine learning models, and one model say, oh, I only trained on 10 data, right? It's the image recognition models. I only train on 10 people, right? I only train on 10 people's faces. And the other machine learning model said, oh, I trained on like millions of people's faces. So which one would you buy? Of course, you will buy the machine learning model that trained on millions of people's faces. It will be more accurate, right? So that should be reflected in the loss function. So for those who trained on millions of data, it should divide the loss function by million, right? So we are tolerable if it makes several mistakes. But if you only train on 10 like people, we should not tolerate it, even if you make one mistake, right? So it's like divided by 10, and 1/10 is quite large, right? So normally in loss function, we should reduce the loss function to what? Here is like a industry standard. So we should reduce the loss function if like if your like a resource if your resource limitation is not considered, we should reduce the loss function to like 10 to the negative power of 6, right? So that is 0.000001. Yeah, we should reduce the loss function to this small. Yeah, this is like an industry standard. So actually it's not that industry standard. It's like it's that if your loss function is even larger than this, you can turn in your homework. Like even the professor will doubt on your results, right? If you say, "Oh, I make the loss like around 0.01," the professor will say, "Oh, you should continue working on that," right? And if you make your loss like maybe like a 0.5, then the professor may say, "Oh, this is like a total garbage. It may be random." So even a random guess can have a loss like closer to that, right? So yeah, so you should make your loss as small as possible. And how to make a loss small? Having more training data, of course, can help because the more training data you have, right? The larger sample size you have, you are dividing a large n, and that really helps on minimizing the loss, right? But of course, having more data is not the only way to minimize the loss. To minimize the loss, of course, like the best way is to make a zero like mistakes, right? If you make zero mistakes, by definition, the loss is of course zero. So you don't even need to care about the sample size. I mean, of course, you should still care about sample size because the sample size is not a standard, it's not an industry standard, right? So if you submit your homework and you tell your professor say, oh, I got a loss function of zero, I only trained on five data, the professor said, even human can read five data and make a correct guess, right? So five data, why would you even bother to use a computer to do that, right? So you need to train at least like I think at least on 1,000 data, right? On 1,000 data, and you get a loss around this, then that's pretty good. That's pretty decent. Yeah. So this is just some vague number or general numbers to get to help you get a general idea of what's a machine learning standard or like how like if you are applying machine learning models, like to what extent should you or what like standards or metrics should you use to guide your development? Yeah. Okay. So now you have a really concrete understanding of a normalize, and using normalizes to help you to get the average loss per sample, right? Per sample or per data. Yeah. Because if you do not divide by n, you get the total loss, and total loss is especially unfair for large training data. Because if you have a lot of training data, you should be rewarded instead of penalized. Okay. So enough on that. Let's go through the review for the 0 1 loss. This is what we taught yesterday, but still, I think we can we can review this and maybe Emma. I think Emma Yu or Emma Shi. So today we only have one Emma. So yeah, Emma. So can you help read this paragraph?
0 1 loss. The simplest loss function is the 0 1 loss. It literally counts how many mistakes and hypothesis function H makes on the training set. For every single example, it suffers a loss of 1 if it is mispredicted and 0 otherwise. The normalized 0 1 loss returns the fraction of misclassified training samples, also often referred to as the training error. The 0 1 loss is often used to evaluate classifiers in multi-class binary classification settings, but really useful to guide optimization procedures because the function is non-differentiable and non-continuous. Formally, the 0 1 loss can be stated as
Okay, cool. You see, even in the lecture notes that it's not non-differentiable and non-continuous, right? So, and I have explained that because in the loss function, you sometimes jump 0 to 1. Okay. Emma, can you also explain what does this mean in your like plain words like this?
um
I mean, you can give a guess since we
so
have, yeah.
it says if like hx I is not equal to y then it's 1 and
Yeah,
otherwise it would be 0.
yeah, cool. So can you explain so let's ignore the 1 over n. So can you explain this as a whole? So what are we doing here?
Dif
Yeah, of course. I mean, you are correct in saying that when these are not equal is 1, when they are equal is 0. and we are adding them all together. So what are we doing by adding them all together? So can you explain this in a more like to a layperson, right? So if someone don't even know machine learning, how do you explain to him?
Like to see like how many um like
Yeah, I think you
where
are on
every
the
single example suffers a loss of one if it's mispredicted and zero other.
yeah, exactly. You're on really on the right track. Yeah. So if I explain to the layperson, it's really simple. I'm just saying, so this function just calculates the total number of mistakes you make, right? Because if you make one mistake, it's one. Is you making two mistakes is two. Making three mistakes is three, right? Because if you don't make a mistake, you are adding zero, right? Adding zero does not count, right? So this whole stuff is not too hard, right? If you explain to someone doesn't even know the machine learning, you say, oh, the loss function. So for zero one loss, the loss function is just the total number of mistakes you make, right? It's just a count, right? It's count of total count of mistake you make, right? That's simple. And we are dividing by n, right? So now we need to modify our language. So it's no longer the total count of our mistake. It's the average number of mistakes we make out of the n data, right? So if we make three mistakes out of five data, then our loss function is 3/5, right? So zero one loss function if you explain in plain words, it's really just the total number of the average number of mistakes you make, right? Do you agree with this? Yeah. So you see, one way to learn machine learning is that you see this is a really like a complicated mathematic expression, right? But the one way to learn machine learning is to explain to try to explain to layperson what the hell is this, right? Yeah, it can be put into much simpler words. Yeah. So it's zero one loss is just the average number of mistakes you make out of all the n data points. Yeah. Okay, but even if you know the plain explanation, but do try to memorize this math formula because it really helps when you write papers, right? When you write papers, you really want to show fancy formulas, right? To show that you are an expert in this field. Even if you are quite new on machine learning, you have just learned three lectures, right? But if you can write this into your paper, someone will say, oh, you have at least trained on machine learning, maybe have already gone through a systematic courses. Yeah. Okay. So the loss function returns the error rate, right? So I said this is like the average number of mistake, and a more accurate word phrases is error rate, right? Error rate is just an average number of error you make, and it's called a rate, right? The rate is usually means average number of something. Yeah. So the loss function here returns the error rate on the data, right? So if you make a three error out of five data, the error rate is 3/5, right? So do memorize this word. For every example that the classifier misclassifies, a loss of fun is suffered, right? Whereas the correctly classified samples lead to zero loss. So you see, zero one loss is like the easiest way to understand the loss function. But as we said, it is not so it is quite easy for human to understand, but it's not like easy for computer to understand because computer like continuous stuff, like differentiable stuff. Because computer knows how to do calculus, computer knows how to do derivatives, and if your loss function is differentiable, will be really good at finding the coefficient to minimize the loss function. That is what so minimizing the loss function is what machine learning is all about, right? So in order for computer to generate the program for us, when we like seldomly use zero one loss. Zero one loss is usually for like beginners, for human beginners, to help you understand what loss function is. And now this is like a very frequently used loss function. And for this one, we will also practice calculating it in this lecture. Yeah, but before that, maybe maybe like let me find some other person. Maybe Andrew, can you help us read this highlighted texts? Yeah.
Wait, me?
Can you help us read this highlighted this part?
Yeah, sure.
Yeah.
The squared loss function is typically used in regression settings. It iterates over all training samples and suffers the loss h of xi minus I yi squared. The squaring has two effects. The loss suffered is always non-negative, and the loss suffered grows quadratically with the absolute mispredicted amount. The latter property encourages no predictions to be really far off, or the penalty would be so large that a different hypothesis function is likely better suited.
Very cool. So maybe Andrew, can you say some properties of this square loss based on, based on this paragraph?
Could I just like
Yeah.
rephrase like the two
Yeah,
things that they
sure. You can
okay.
replace the two things. Oh,
So
sorry.
like
Yeah.
um like the value we get out of the squared loss function is like just like it's not exactly like a difference. It's like the direct difference because it's like not negative, which is like the first one.
Yeah. So
And then
and
like it also
yeah. Yeah. What's the other one? Yeah.
uh it also like really discourages like being off by a lot, even like one time. I think it like encourages like all the points being off by a little bit rather than like 1 point being off by a lot.
Yeah, exactly. So this is one thing that 0, 1 loss doesn't catch, right? So for 0, 1 loss, if you are wrong, then we add one. We don't care how wrong you are, right? Say for example, for this example, so 0, 1 loss is often used in like a binary classifier, because binary classifier like the answer can be either 0 or 1, right? So we don't care how wrong you are. You are making an error of either perfect or just one error, right? But what? But say if we are in a multi-class classifier, right? So like our y can be our real y can be 1, 2, 3, 4, 5, and say it's 1, 4, 5, 2, 3, right? And if we apply h on x, and our prediction gives correspondingly, say gives 2, 4, 4, 1, 3. If we are using 0, 1 loss, can someone calculate the 0, 1 loss in this example? Mm, this is quite challenging. Maybe Mark, can you give a maybe give a way? You don't need to calculate it exactly, but give a way on how to calculate 0, 1 loss in this example. Mark, can you calculate the 0, 1 loss in this example? Um, maybe like Phoebe? Yeah, let you take the challenging task. Phoebe, do you know how to calculate 1, 0 loss in this example?
No.
So let me give you a hint. So remember what is 0, 1 loss? We just said it's error rate, right? So what is error rate? It's the average mistake you make, right? So how many? So now tell me how many mistakes you make in this example. Remember y is the true answer and h is your prediction. How many mistakes you make?
Uh, 3.
Exactly. So then what's the error rate? So you make 3 mistakes. What is the error rate? Put it into more simpler phrase. So what is the average number of error you make? Average number of mistake you make. So total mistake is 3, right? So what is the average mistake? Let me
3
give you
divided,
yeah. 3 divided by what?
divided by 5.
Exactly. Yeah, that's the error rate. See, 0, 1 loss. Why we introduce it as the first loss function? Because it's very easy to calculate. It's just
Okay.
error rate. Yeah. So you make 3 error out of 5 numbers, right? out of 5 data points, then the 0, 1 loss is just 3/5. See, you don't need even a pen. And this is a one very good example where you will encounter in your college that the formula, right? The formula is really complicated, but the calculation is like extremely simple, right? It's surprisingly simple. Yeah. So this is one cases. Yeah. Okay. So, and of course, you can use the formula to do the calculation instead of using error rate. So how do we use formula? Using formula, we compare 1 and 2, and we see, oh, they are not equal. So what do? We add 1, and we sum. 4 and 4, they are equal. So what do? We add 0, right? We add 0. And 4 and 5, they are not equal, add 1. And the 2 and 1, they are not equal, we add 1. 3 and 3 is equal, we add 0, right? And at the very end, we normalize it. By normalize, it means dividing by n. And what is n here? We have 5 data, so n here is 5. So 1 plus 0 plus 1 plus 1 plus 0 divide 5 equals 3/5, right? So you see, we can still get the same answer by using the formula. But if you really understand the formula, you know that we are really just calculating the error rate. Just count the number of errors and divide by the total numbers. So 3/5. See, very simple. Okay, so now let's use the same example and let's calculate the square loss. And to make your life easy, let me put the square loss function here, and let's put them side by side, side by side. Okay. Yeah, so this is square loss, right? Okay, so I need volunteer to calculate the square loss here. Maybe like Hector. Can you calculate square loss in this example? Don't give the answer, but you can just give the steps. Yeah. The formula is on the right hand side.
Oh,
So what is hx and what is y? You see hx here and y is here, so plug in number. Yeah.
we plug every set into it.
Yeah, exactly. So you can just say some stuff to begin. Yeah. Like what's the
Okay,
first?
so we try the first set, like
So what is the first part? I mean, this is a sum.
uh
Yeah. I mean, the first part in 0, 1 loss is 1, right? Because 2 and 1 are not equal, so we have a 1 here. But in square loss, it's not a 1 anymore. It's a hx minus y, and you need to square it, right? So what is that? You can just plug in number. You just need to tell me the first term.
so 2 minus 1 squared.
Exactly. Yeah. So you see, we will have 5 terms also, right? So this means summing, right? This is a sum notation. It means summing from 1 to n. In this case, it's summing from 1 to 5. Yeah, 1 to 5. Okay. So the first term is hx1 minus y1. So hx1 is 2, y1 is 1, right? So it's just 2 minus 1. And what? And square. And then what? And finding the hx2 and y2. hx2 is 4, and
Oh,
y2 is 4, right? So 4 minus 4 squared. So yeah, let me stop here for a bit. And of course, you will plus a third term. Yeah. So what do you find is similar between the square loss and the 0, 1 loss? I mean, of course, they have a lot of difference. So what's the similar thing? Hector, can you answer this?
they both calculate the like they both show how like the wrong term you got, but the square loss was like bigger.
Yeah. Like that's correct, but the thing I think is like more obvious is that both square loss and 1, 0 loss will give 0 if you make a correct answer, right? Because you
Oh
see,
yeah.
if 4 and 4 agree is 0, and if 4 and 4 here, we plug in here, it's like a 4 minus 4 square. So that is the essence of loss function. So for any loss function, it should be 0 when what? When you are making a correct prediction, right? So loss function should never penalize you, if you make a correct prediction, right? So you should be always 0 if hx equals y, right? So there will be millions of loss function out there. So you see, people are publishing artificial intelligence publishing really fancy machine learning articles, right? So they are just publishing all those kind of machine learning articles. So what actually did they do? They just design a specific or clever version of loss function, and they say, oh, with this loss function, I can get a new model with higher performance, with greater performance, right? But whatever loss function they design, whatever clever modification they apply, one thing they cannot change is that if you make a correct prediction, your loss function on that part, on that term, on that specific data point should be 0. Because we should not. So loss means penalize, right? It means you lose, right? Loss means you lose and penalize you. If you make a correct prediction, we should not penalize you. So it will always be 0 on the term where you make a correct prediction. Yeah, so that is one thing. And the other thing I think is also mentioned in the paragraph here, right? It's non-negative. So why would the loss function be non-negative? Can anyone answer this question? Maybe Phoebe, can you answer this? So we just said that loss function can be 0 when you make a correct prediction. So why has it to be non-negative? What will happen if it becomes negative? Any guess?
I have no idea.
Okay, okay. I mean, this is quite hard. It needs a lot of math intuition. Yeah, let me put it this way. I hope like after my explanation, you will find it more intuitive. Yeah. So the thing is like this. If so loss function is like building, right? Whenever you make a mistake, your loss function grows, right? Increase. So everyone agrees on this, right? So like in either 0, 1 loss or in square loss, if you make a mistake, right, you get a positive loss, right? And if you make a correct prediction, you get a 0 loss, right? So we will not penalize you. But if you get a negative loss, what does that mean? That means we are rewarding you. We should never do that, right? Because like one correct prediction should not reduce the loss on your previous mistakes, right? It's not like I make a lot of mistakes and hooray, I get one correct result. I can neglect all the mistakes I make, right? That should never happen because your correct prediction could be just pure luck, right? You are out of pure luck, you get one thing correct, and then like it's like answer. It's like when you answer an exam, right? If you get one question right, you get the points for that question. No teachers will say, "Oh, you get this question correct, and all your previous incorrect question, I will give you points on that." That's not even possible, right? So if you answer the previous question incorrectly, we should deduct points, right? That incur a loss, right? Deduct point for your previous incorrect questions on exam, that incur loss. And if you answer one question correctly, we do not deduct your points. But we should not like okay, you answer this question correctly and all your previous mistakes, we ignore that. No professor will do this, right? Yeah, the same logic applies on loss function. In loss function, if you which why should the loss function why is the every term every part, right, every term, so every term in this sum, right, why is every term in this sum non-negative? Because we should never ever reward you for making one question correct, or making one correct prediction, right? So making correct prediction, the best result you can get is a 0 loss, right? So we won't add anything to the loss because you make it correct. But we should never make a negative. Making negative is like you are erasing your mistake. You are erasing the history, right? So loss function. So this also explains why machine learning is clever. Why machine learning can learn history is through loss function. Because the loss function, if you ever make a mistakes in the history, it never goes, right? It never goes away. It gets sums up in the loss function, right? You already make three mistakes, then the loss function is already adding three error term in the sum, right? So it can either be one in the case of a 0, 1 loss, or it can in this case it's like three squares, right? Three stuffed squares and already added here because they are making mistakes, and for the correct prediction you add 0 here, right? So we can ignore all the correct prediction, but since the loss function can never have a negative terms, so we never erase the previous mistakes. So that's how the machine learning can learn from previous mistakes, can learn from all the previous mistakes. Because if you have a negative stuff, all the previous loss built up, right, got canceled out because you add a negative number. So you already incur three loss and you add the negative three, and all those loss just become 0 and just got thrown away, and the machine learning learns nothing. The machine learning will say, oh, if you make one prediction, all the history gone, right? You are good people, right? It's like it's like a criminal, right? A criminal has done a lot of crimes, and he just at one time did not perform any crime, and then you say, "Oh, I'll clear your criminal history." That's not even possible, right? So this is the intuition. Yeah. So this is why any terms in the loss function cannot be negative, because adding negative is reducing loss. Reducing loss is clearing history. It's like erasing the mistakes you made previously. That is that is something that we really don't want to do. We want the machine to learn from your mistakes. You should never erase your mistakes. Okay. Yeah, so that's a very important thing on loss function. You see, we have a talk about loss function for two entire lectures. Yeah, because it's very important. And let's continue finish our square loss function. So we already add two terms, and I think maybe the third term is should not be hard to write. Maybe Andrew, can you say can you give us the third term and fourth term? Maybe also the fifth term in this loss function.
So like 4 minus 5 squared.
Yeah, exactly. So the first one, can you also give the fourth and fifth?
1 minus 2 squared.
Yeah,
And then the last one would just be 3 minus 3 squared.
exactly. Okay, cool. And maybe Chloe, I think so you see this is a square loss function, right? But we are still missing one thing. So what do we miss? Chloe? You can compare with this formula. We are still missing one part. So what should we apply on this? Is this a loss we want to get? Um, Maybe Mark, can you answer this? Is this a entire loss, or should we modify it a bit? Okay, maybe Hector. Hector, can you answer this? Is this like the final answer for the square loss?
We divide by the total.
Yeah, we need to divide by the sample size, right? The training size, which is 5, right? So this is what we call normalize. We need to normalize the loss. And why do we need to normalize the loss? Because still as a 0, 1 loss, right? So for the square loss, you are always adding non-negative stuff, right? So of course, if you have a hundred data points, and of course you are making some mistakes, and you will add a lot of stuff, right? Adding a lot of non-negative stuff will make your loss really large, and we don't want the loss to increase with the sample size, because large sample, large data collections, right? A large number of data means a good thing, and we should reward that, right? So if you have 100 data to train, we will divide by 100. If you have 1,000 data to train, we will divide by 1,000. That's what we call them normalized. Yeah. I think that's all the part of the loss function here. And let's take maybe a 10 minutes break. And yeah, let's take a 10 minutes break and I will mute myself and stop the recording. And in the next lectures, not lecture, not the next lecture, is in the second part of our lectures. I will go through we still have one absolute loss which is quite similar to the above to go, and then I will go through the generalization because generalization is pretty hard to understand. Yeah. So yeah, let's take a 10 minutes break. And let me stop share for a bit.